Okay, so in this video we're going to talk about solving two variable systems of linear equations using the method of elimination. So in our first video we solved using graphing. So remember, the solution to a system of linear equations in two variables is where the graphs intersect one another, where the lines intersect one another, okay? And we saw that visually with graphing, okay? But then last video we talked about solving using substitution, which is a purely algebraic way, okay? But that still is what you're finding, the point at which the lines intersect, okay? And in this video we're going to talk about solving using elimination, okay? Now remember, substitution was best used when one of the variables was already solved for, or one of the variables in either equation had a coefficient of like 1 or -1, which means you can quickly solve for it and use substitution. Elimination is best when that's not the case, okay? When it's not too particularly easy to get a variable isolated and solved for, or when you solve for that variable you're just dealing with a bunch of fractions, because people don't like fractions, all right? That's when mistakes are generally made by a lot of people, all right? So elimination is best used when we simply just cannot solve for a variable nice and cleanly, okay? And the way we want it set up is just like this, where both equations are in what we call standard form, okay? What I mean by that is that we start with an x, then we have a y equals constant, okay? So we have x, y constant, x, y constant, okay? Now, to use elimination, what we need to do is to get the coefficients on one of the variables to be the same but opposite signs, okay? Because when we add those two equations, that variable's going to cancel. So for example, if I look at this equation or this system here, I have a 5y and a -5y. That's exactly what I want, okay? Because now what we can do is we can add these two equations together and the y's are going to eliminate one another, hence the term elimination, okay? So I'm going to go ahead and show you exactly what that looks like. So I'm going to add these two equations together. So I'm going to have 5x plus -8x. This is going to get me -3x. 5y plus -5y, those cancel out. That gets me 0. So the y's are now gone, leaving me with just x. So now I have -3x is equal to 5 plus 16 is 21. So just like that, our y's are gone, and we can quickly solve for x. That's when elimination is very, very useful, okay? And especially once we get into three variable systems, elimination is kind of the preferred method, okay? So but back to this problem. Now we have -3x is equal to 21. I can divide each side by -3, and we're going to get x is equal to -7, okay? So once again, remember our solution is always going to be the ordered pair, the point x comma y. Well, we have our x is -7. Now we have to find our y, and to find our y we actually do have to use a little bit of substitution, okay? So I now know that x is -7. I can take this -7 for x and substitute it in either of my two original equations. I'm going to substitute it into the first equation, okay? So with that said, I'm going to have 5 times x, which I just found is -7. So 5x plus 5y is equal to 5, and now I can go ahead and solve for y, okay? Because I'm going to have -35 plus 5y is equal to 5, and now I can add 35 to each side to start getting y by itself. So I'm going to have 5y is equal to 40, and that 5 is multiplying y, so I need to divide each side by 5 to get rid of that. 5 divided by 5 is 1, so I'm going to have 1y, that's what I want, is equal to 8. So that gets us our solution of -7, 8. So that is the point at which these graphs would intersect one another, okay? So that was a little bit more of a basic problem where our coefficient on one of our variables, in this case y, they were already kind of set up to where when we add them together they cancel out immediately. I want to take a look at an example that doesn't do that. So if we take a look at this example here, okay, we have 6x minus 5y is equal to 14, and 3x plus 4y is equal to 20. Okay, now it's not that you cannot cancel out either variable, because you can, okay? I can go ahead and find out a way to cancel out the x's. I can find out a way to cancel out the y's. But in some cases, one variable is going to be a little bit easier to cancel out, okay? Now, the way we think about this is the least common multiple of each coefficient. So if I look at x, I have a 6 and a 3. The least common multiple between 6 and 3 is 6, okay? Whereas the least common multiple between 5 and 4 is 20. I would have to multiply both equations. I would have to alter both equations in answer to cancel out the y's. Okay. However, I can quickly get this to become a negative 6x by multiplying it by negative 2. So I'm going to go ahead and multiply the entire second equation by negative 2, because once I do that, and let me just go ahead and rewrite my first equation for organizational purposes, okay? Because once I go ahead and I multiply this entire equation by negative 2, the x's are going to cancel out, because negative 2 times 3x is negative 6x, and that's exactly what I want, because now when I add the two equations together, the x's are going to cancel. But I can't just multiply one term in the equation by negative 2. I got to multiply every single term. I got to do it to both sides, okay? So I have negative 2 times 4y, which is going to get me negative 8y, and negative 2 times 20, which is negative 40, okay? But now, as you can see, when I add these two equations together, 6x plus negative 6x cancel out. So the x's are gone. Negative 5y plus negative 8y is negative 13y, and 14 plus negative 40 is going to be negative 26, okay? So that's where elimination is really, really useful. I can quickly multiply one or both of the equations by some number, okay? So where now I'm going to have the exact same coefficient on one of the variables, 6 or negative 6, kind of the opposite sign, okay? And then I add the equations together, because now this is real basic. This is straight from like Algebra 1. Negative 13 is multiplying y, so I'm going to go ahead and divide each side by negative 13. And that's going to get me y is equal to 2. So I know y is 2. Now I just got to figure out what x is. And to get that, I just need to use some substitution, okay? So I need to take this 2 for y and substitute it into either of these two equations. I'm going to go ahead and substitute it into the second equation here. So I'm going to have 3x plus 4y, which I just found is 2, is equal to 20. Notice I'm using the original equation, not the altered one. And it didn't matter if I used the first equation or the second equation. Just go ahead and pick which one, okay? I went ahead and opted for the second one just because I'm dealing with some smaller coefficients. 3 and 4 is definitely less than 6 and negative 5. I'm going to be dealing with smaller numbers, okay? So once I do this, I'm going to get 3x plus 4y. Well, that gets me 8 is equal to 20. And now I need to subtract 8 from each side. So I'm going to get 3x is equal to 12. And now I go ahead and divide each side by 3. I divide each side by 3. Whoops. I divide each side by 3 to get x is equal to 4. So my solution is going to be the point 4, negative 2, 4, negative 2, okay? So that's how we use elimination, okay? Now I do want to go over just one special case just to make sure we're all on the same page. So let's go ahead and take a look at this example here. So in this example, we have 4x plus 2y is equal to 8, and negative 6x minus 3y is equal to negative 6, okay? And in this equation, there's not necessarily going to be one variable that's easier to cancel out. So in the previous problem, I was able to just multiply one of the equations to get kind of the opposite coefficients that I wanted, okay? And in the first equation, I didn't need to alter any of them. I already had a 5 and negative 5y. In this case, that's not going to be the case, okay? So it doesn't matter which variable you choose to cancel out. I'm going to actually choose to cancel out the y's, okay, just because I'm dealing with smaller numbers. So 2 and 3, the least common multiple between 2 and 3 is 6. So in order to get that, I'm going to multiply this equation here by 3. And when I do that, I'm going to get 12x plus 6y is equal to 24, okay? And if this is a 6y, I'm going to want this to be a negative 6y. So I can multiply this equation through by 2, okay? So I'm going to have negative 12x minus 6y is equal to negative 12, okay? And when I add these equations together, something happens. 12x minus 12x is 0. 6y minus 6y is 0. 24 minus 12 is 12. So what I get is 0 equals 12. And if you saw the substitution video, something special happens, or there's a special case where all your variables cancel out. And once again, all the variables cancel out. All the variables canceled out. Okay. Now, when that happens, remember there's two possibilities. We can either have a no solution or infinitely many solutions. No solution means that it's a pair of parallel lines. They're never going to intersect. So since they never intersect and the solution is where the graphs intersect, there would be no solution. Or they're actually the exact same line. They're on top of one another, which means infinitely many solutions. Okay. Now remember, if all your variables cancel out, and you're left with a statement that is not true, that is false, okay? So in this case, 0 equals 12. This is not true. This is a false statement. If all your variables cancel out and you're left with a false statement, there is no solution, okay? There is no solution, because if we were to graph each of these, what we're looking at is a pair of parallel lines that are never going to intersect, and since they're never going to intersect, there is no solution to the system, okay? This is a special case. If you want to go back and watch the substitution video, I talk a little bit about the infinitely many solutions, but those are the three main ways we're going to cover solving systems of equations, okay? In our next video, we're going to talk about solving 3 variable systems, okay? So make sure you check that out. We're going to be using elimination quite a bit.